So now I'd like to point out that we have not furnished these axioms and definitions of lines and distances and whatnot with enough power to prove the things that we intuitively believe. And the geometric things that we intuitively believe are generally the what we call Euclidean geometry, that straight lines behave in the ways that we expect them to have infinitely many points and certain things like that. Those are sort of all embodied and encompassed in what we call Euclidean geometry. We don't have Euclidean geometry yet. In fact, we're kind of far from it. And here I'll point out that we could already violate certain sort of simple things that we tend to expect from notions of distance and whatnot. So, for instance, if B is between A and C, as I have in this little picture here, B is between A and C is between B and D, you would expect it to be true that C is between A and D. And as I've drawn it, that looks true, but I can pick values for my distance metric which satisfy the axioms of a distance metric, but does not satisfy that fact. In doing so, I produce what's called a counter-model. So, for instance, suppose I picked the distance between A and B to be 1, B and C 2, and therefore if I want betweenness to hold, I pick AC equal to 3. Now I'll do the same thing to get betweenness for C between B and D. I already know BC is 2. I'll pick CD to be whatever I want, and then choose BD so that I make sure betweenness holds. Now, what about C being between A and D? Well, I'd have to choose a value for the distance A to D. Before doing that, let's look at what I already have in the equation that's relevant for the distance from A to D and betweenness, which is AC plus CD. We can look at the values we've chosen already and see that those sum up to 4. I will therefore get betweenness just in case I pick AD to be equal to 4. If I pick it to be anything else, and I am free to pick it as anything else, then betweenness will not hold. What this tells us is, well, there are two lessons we could perhaps learn from this. One of which is that if we want all of the intuitive properties of Euclidean geometry, then we need more axioms to express them and capture those intuitive properties. The other spin that we could give this is that we might choose other axioms to give us an alternate geometry. A common example is spherical geometry. It's not the only example, but if you had a sphere and you picked your points to be on the surface of this sphere, you would get sort of unfamiliar properties. Like, for instance, if you drew a triangle, the interior angles would not sum up to 180 degrees the way that they do in standard Euclidean geometry. So anyway, we won't be going into that now, but this is all set up so that we will eventually be able to play with the axioms, choose different ones, and see the different kinds of geometries that come out of them. But in any case, in the next video, we'll continue adding axioms so that we build up Euclidean geometry first.